Hello, and welcome to this introduction on dynamic algorithms. Algorithms, as we usually meet them, is what we call static. By that we mean that we initially are given some input, and our task is to compute some function of the input as output. In the older days, when Dad was young and started at computer science, programs were written using punch cards. In this process, we had the same idea as we do with our static algorithms. We put in our card which contains our input. It crunches and calculates, and after a couple of hours the output is given. If you then had some syntax or compile errors, you would see them and you could get them fixed. Then you would have to do the entire process all over again. Today we have interactive terminals and can do this input without punch cards, but still it's the same. We give the algorithm some input and we get a specific output. So what we would like instead is not to reload the entire thing, but change the specific parts of our input, so our algorithm should allow changes, hence being dynamic. As an example, consider the case of x being a string. Naturally, one may allow change, insertion, and deletion of letters. If x is a graph, one may allow insertion and deletion of vertices and edges. What the dynamic algorithm gives us is the ability to change data over time, see what effect it would have to change the data, like strategic games in chess, to calculate the different outcomes in the next 4 moves. There are 2 groups of dynamic algorithms. Partially dynamic, where we can change things, but we cannot reverse these changes. Think of a graph where we would be allowed to insert edges, but not delete edges. This is also called incremental. We also have fully dynamic, is maybe not surprising, where we are allowed to revert changes. So in our graph problem, we may insert and delete edges. In general, we want this implementation of a data type to solve dynamization with the following operations. Init, initialize our input to some fixed value. Change our data x somehow using d. Query, answer some question about our function. Now I believe it's time to do an example. We'll take a problem called the balanced parenthesis problem. The question we want to answer is this string containing n parentheses balanced? Meaning every starting parenthesis have a matching closing parenthesis on its right. So what would the naive way to do this be? We could start by having a counter. Every time we meet an opening bracket we increment and decrement every time we meet a closing. This would indeed show if there is an equal amount of opening and closing parentheses, but there is an issue. Think of this next example. This would resolve to 0 but does not contain a balanced sequence of parentheses. Now we could try writing this as a context-free grammar. This is a well-formed description of the balanced parentheses. From here we can define a push-down automata that will check if our expression is valid. So the idea is that we push every starting parenthesis onto the stack, and every time we meet a closing parenthesis we pop one off. Here we will quickly discard the negative test case because we will try to pop something off the stack that isn't there. From our general notation we have that init s initialize the input string s. Change I. The only logical change is to revert the ith parenthesis in our string s. Our query is to decide whether s is perfectly balanced or not. Now that we got a working algorithm, we can begin focusing on execution speed. To answer the query takes O of n time, which is pretty good. But what happens if we change some index in our string? We have to spend at worst O of n time again to calculate the entire input. Now it's time to do this better. Instead of doing this, we can do a divide, solve, combine algorithm. So what we do is we build a balanced binary tree, and we count left and right parentheses. The actual algorithm is written like this, with a function called match. Returning back to our runtime, initialization still takes O of n time. We have to run the sequential algorithm and store all intermediate match values. If we decide to reverse a parenthesis, we only need to recompute O log n match values, which takes O log n time. We can answer the query in constant time by just looking at the stored result in our bottom root. Now let's take another example of improving algorithms using dynamic algorithms. We consider dynamic maintenance of connected components in a graph. We'll only consider the incremental version of this problem. Our data type maintaining our undirected graph G supports the following operations. Init, G becomes the empty graph with n vertices and no edges. Insert, add an edge between V and W to our graph G. Connected reports whether V and W are in the same connected component in our graph G. A trivial solution to answer our connected call is to perform a search algorithm. This could be depth first search. Our structure for our graph could be an edge list and an incidence matrix containing the information needed in our graph G. That would result in constant insertion and O of m time for connected analysis. This is called a lazy attempt because we don't compute the result right away. We actually do nothing. Another trivial solution is recomputing the connected components for each call of insert. That is called an eager approach because we do everything as soon as we have the information. A better solution is provided by the union find data structure, maintaining a partition of set into classes while supporting two operations, getting the number of classes containing a specific element and uniting two classes into one. The classes correspond to connected components in our graph. The solution for our partially dynamic graph problem will have this amortized time complexities, where n is the number of vertices in our graph. Until now, we have only discussed this problem as a partial dynamic problem. This is because if we wanted to solve the fully dynamic version, we must implement an additional operation called delete, which will remove edge between V and W from our graph G. The too naive solution would still work because deletes get the same complexity as insert. But the union find structure is no longer applicable. This is a very hard problem to solve, and the best solution so far is by Mikkel Thorup, where he has obtained expected amortized time of O log n log n to the power of 3 per operation using randomization. Thank you for watching this introduction. More videos will be up later, and if you have anything specific you would like explained further, or have any questions, leave a comment or write to me using the email in my description.